Question number 4. When an alkane is burned in excess, that means a plentiful supply of oxygen, they produce carbon dioxide and water. So while there's an excess, lots of, a plentiful supply of oxygen, it's called complete combustion, and carbon dioxide and water is made. Incidentally, if there isn't an excess of oxygen, or not a plentiful supply of oxygen, not enough oxygen, it produces carbon monoxide and water, like there is in a faulty gas boiler where there's not enough ventilation oxygen coming in. It can also make a black solid like it does coming out of a car exhaust engine, called carbon as well, if there's not a plentiful supply of oxygen. Anyway, there's an excess, a plentiful supply of oxygen, so it's going to make carbon dioxide and water. Complete combustion rather than incomplete combustion. Complete combustion making carbon dioxide and water. Propane. What's propane? C3H8. It's got single bonds, so the general formula CnH2n plus 2. 3 carbons in propane. Double it, add 2 is C3H8. Reacting with oxygen, we'll come to the 5 in a minute. It makes carbon dioxide and water. We'll come to the 3 and 4 in a minute. So I've got C3H8 plus O2 making 3 CO2 and 4 H2O. The only place that the carbons can go is into the carbon dioxide, so 3 carbons must be 3 CO2. The only place the H's can go is into the water, so 8 H's must be 4 H2O to make 8 H's on either side. And now we can balance the oxygens. Let's work out how many oxygens we've made. 3 times 2 is 6. 4 times 1 is 4, 6 add 4 is 10, a number multiplied by 2 to equal 10 is a 5. Question 4.2 is a little bit of maths. It says we've got bond enthalpy data and we've got an expression for the bond enthalpy is minus, and then in brackets 496N plus 2O2. That's an expression for the bond enthalpy, and the bond enthalpy of combustion is minus 6650. In other words, this expression equals minus 6650, and you need to solve it for n to work out how many carbons there are. N carbons, we're going to work out n. So let's have a look at this. Enthalpy of combustion equals minus 6650, and it equals this expression, minus 496 plus 202. You may know from maths that if there's a brackets, then everything, the minus applies to everything throughout the brackets. So minus 6650 equals minus 496, and that's a plus, but it gets a minus 202. Now what I'm going to do is I'm going to rearrange. If you look at how I've rearranged, I've taken the minus 469n across the other side of the equals sign, so a minus then becomes a plus, so it's 496n, and I've taken the minus 6650 across to the right hand side of the equals sign, and that becomes then a minus becomes a plus, so it's minus 202 that stayed where it is, and a plus 6650 gone across to the right. So 496n, let's do this little calculation first, equals 6650 take away 202, which is 6448. Divide both sides by 496, so n equals 6448 divided by 496, it equals 13. So I've got 13 carbons. I know the general formula for an alkane is CnH2n plus 2, so I double the 13 to 26, add 2 and it becomes 28. Its empirical formula is C13H28, and that's probably its molecular formula as well, I would suspect. Suggest one reason other than the use of mean bond enthalpies why a value of the enthalpy of a combustion of a liquid alkane is different from the value obtained in the expression. Tricky question this. The liquid needs to be heated and turned to a gas before it will combust. This needs to be a gas, so your fuel needs to be evaporated into a gas before it will actually react with oxygen and burn. So the liquid alkane actually needs to be evaporated and turned into a gas before it'll actually burn. So there's another factor in there, that the value, which is the enthalpy of combustion, the energy that's given out when you burn it, here is not going to equal the practical value, because you've also got to evaporate it before you actually then combust it. So there's heat energy needed to turn the liquid alkane into a gas before it's combusted. A tricky question, that. Here now we've got some values. So we've got enthalpy change when you combust each of these alkanes, and we're missing a value of propane. We've got to plot this on the graph, and then we've got to use the graph to work out the value for propane. if you plot it on a graph and you put the points there, you'll get a mark for the points. And then if you put a line through it, you might be tempted to put a straight line through it as a line, draw a line of best fit. That's actually wrong. A line of best fit doesn't have to be a straight line. If you look, you get a better line of best fit by doing a curve. It can't just be zigzagged. You can't just join all the points with a straight line. It's got to be a line of best fit, but a line of best fit could be a curve, and I think a curve fits that better. As long as it's a smooth shape, either a straight line or a curve, that can be a line of best fit. So I think your line of best fit is sort of like that, and then when you read from the graph, methane, ethane, propane, butane, pentane, 1 carbon, 2 carbons, 3 carbons in propane, 4 in butane, 5 in pentane. So we've got 3 carbons here. We go down until a line and we read it off here, and I think it's minus 51.4, something of that nature. We've got spoilers here, sorry about that. When isooctane is burnt, the enthalpy change is minus 47.8 kilojoules per gram. That means when you burn 1 gram of this isooctane, it releases, the minus means it's exothermic, gives out 47.8 kilojoules of energy, 47.8 thousand joules of energy. It's liquid at room temperature with a density of 0.692. And we've been given a volume. Why are we given density? Well, density is mass over volume. That's the only equation we know, and that must be the equation to use then if we're given density. Otherwise, they wouldn't give us density. Density is mass over volume. Look at the units of density. It's in grams and it's in centimeters cubed. So the volume needs to be in centimeters cubed to match this value. I've been given 1.00 decimeter cubed, so I've got the volume, but it's in decimeter cubed, and it needs to be in centimeter cubed to match that centimeters cubed in the density value. So how do I convert 1 decimeter cubed into a smaller unit value of centimeter cubed? Then I multiply by 1,000. So 1 decimeter cubed is 1,000 centimeters cubed. So now, density is 0.692. The mass, I don't know. I'm not given the mass. I think that's what I've got to work out. Divided by the volume that needs to be in centimeters cubed to match the units of density, divided by 1,000. Mass equals 0.692 times 1,000. So I've multiplied through by 1,000. And that will equal 692 grams. And it's in grams because the units of density are in grams. So the enthalpy change now tells me that I have 692 grams. The enthalpy change is minus 478 kilojoules when I burn 1 gram per gram. So minus 478 kilojoules per gram. Grams to the minus 1 means that you're burning 1 gram. And so for 692 grams, it's going to be 692 times the value when I've burnt 1 gram. So minus 478 times 692 is 33077.6 kilojoules. The answer should be in the same number of significant figures as the other values. 1, 2, 3 figures. 0 doesn't count to the left. 692 is 3 significant figures. 1.000. I've got to try and get it to 3 significant figures. I'm never going to get this to 3 significant figures, but I need to get it to 3 numbers at least. I need to round it up. 331, 3 whole numbers, and then with 2 zeros at the end. That's the best that I can do.